Hello, my name is Landon, and this video is on nuclear decay. So before we can talk about nuclear decay, first of all, what is a nuclear reaction? So this model right here should look very familiar. This right here is the Bohr's model of an atom. So right here we have electrons. We have these orbitals, these just representational orbitals, not actual like SPDF orbitals. And we also have these neutrons, and we have these little plus particle protons. So when we're talking about a nuclear reaction, we are talking about a reaction that involves the nucleus of an atom. So instead of having a reaction that happens between two different particles or two different elements, instead we have it interacting with itself, either by ejection of a beta particle or capture of an electron. Whatever it has to do with the nucleus. So now that we have a little refresher on the atom, what is the difference between a chemical and a nuclear reaction? As I said earlier, a nuclear reaction is a reaction that occurs within the nucleus of the atom, while a chemical reaction is a reaction that occurs between different particles. Here we have X representing a particle, and we say it turns into Y mainly because it's changed into a different element. This right here is the general equation for something called an alpha particle decay. So we can see right here we have A, which represents the total number of, or the mass number of the particles. So that's going to be Z, which is protons, plus N. And then we have Z, which is going to be number of protons, and then we have the identifier of the element represented here as X. Now in the case, we'll talk about this later, that Z is too high, we will undergo something called alpha particle emission. An alpha particle is as represented here, it is just a helium atom with no electrons, so we could even represent that as He+, where you can see it has two protons, therefore this is the atomic number, and it has two neutrons, as we can see, because remember, this atomic mass is going to be the protons plus the neutrons. And then we can see the particle it creates. Since we just lost 4 particles in total, this will in turn yield a -4 from the overall product. And that is not right. This is supposed to be Z. Z minus 2 particles because we just lost, again, 2 protons. As for, we have the chemical reaction over here. In this case, this is just representing a double displacement reaction. We have A and B bonded together, and then when switched in solution, we have the C and A bond together, and then D and B bond together. Now, the important thing to note here is that no matter what, there is always conservation of matter. So here, the conservation of matter is represented by, there is still one A on this side, one B, one C, one D, and those particles still appear on the other side of the reaction. The same goes for this. We can see that inside of this is kind of the combined particle of both the, in this case, beta particle and the resulting element. No matter what, this side is equal to this side. Now that we have that down, we can move on to the different decay types. So let me zoom in on this. So first, the first decay type we're going to talk about should look very familiar. That's what we just talked about, alpha decay. Alpha decay involves the emission of an alpha particle or positively charged helium atom, and it therefore yields a new element that has an atomic number that is 2 less than it was before and an atomic mass 4 less of what it was before. So here's a visual representation of that. It has a decreased A value of 4 and then a decreased Z value of 2. Now the second type of radioactive decay would be beta decay. Beta decay involves the ejection of a high-speed electron from the nucleus. So we can see that we have a Z value, and instead of it decreasing like in the alpha particle emission, we have an increase by 1. Why increase by 1? So this little particle over here, that's representing a neutron. And so that neutron is going to eject a negative particle. And therefore, since we know that a neutron is pretty much just an electron plus a proton, it will leave us with a proton. And since protons are counted by using the Z value, we're going to increase the Z value by 1. So now the next type of radioactive decay is going to be gamma decay. Gamma decay occurs when you have a very high energy electron jumping down a massive amount of energy levels, and therefore releasing a very high powered light wave or light packet, otherwise known as a photon. And pretty much the result of this is unchanged. You only have energy being released. You do not have a decrease or increase in any of the subatomic particles. Next, let's talk about positron emission. Positron emission is the ejection of a positively charged electron, and this is ejected from a proton. So if we have positive go away from something that's only positive, we are therefore going to be left with a neutral atom. So, or not neutral atom, neutral subatomic particle. So if we look at the results of that, we're going to have a decrease photon value of 1 because we just lost a photon or proton, and we are then in turn making a neutron. And because we're losing one here and adding one here, that A value is not going to change. And then finally, we have electron capture. Electron capture has the exact same effect as positron emission. As you can see, these little things right here are the same. And the only difference is that instead of turning a proton into a neutron, we're going to turn a proton into a neutron. It's the same. So, but instead we're doing it by two different methods. Instead of ejecting something, we're going to take something from the orbital down into the nucleus and create a proton or a neutron by canceling out the charge on a proton. So you can see instead of a positively charged electron being ejected, we're going to have a negatively charged electron, so just a normal electron, not a positron, entering the nucleus, and therefore going to neutralize one of the protons, therefore decreasing the Z value, and therefore going to increase the N value. But since we decreased one here and increased one there, that A value is going to go unchanged. And we will see inside the next couple practice problems that this right here, these two forms of decay are very similar. And, well, they are very similar, and that usually a element will have a preference for either or, but when just kind of predicting what type of decay it will go through, either one is fine. So there are a few more things we need to talk about before we go on to some practice problems. One of those being the N to Z ratio. So what is the N to Z ratio? Well, as you can see, as denoted by my lovely notes right here, the Z, as we've been talking about, is the number of protons, and N is the number of neutrons. So when we're predicting what type of radioactive decay we should expect a certain nucleus to undergo, we must kind of take into these rules, these general guidelines into account in order to predict that. So if we have any Z value that is greater than 83, so if a nucleus, in other words, if a nucleus has a greater number than 83 protons in its nucleus, we should expect it to always undergo beta decay, since this right here gets rid of the most protons and neutrons as fast as possible. So in order to make an atom more stable, we want to kind of keep it below this number, either that or keep it within its band of stability, which we'll go down and see in a moment. So now in the case that we have a high N to Z ratio, so when we calculate this out, this is kind of the exception. If you have this, then that right there off the bat should tell you that it's alpha decay. If you don't have this, if the Z number is less than 83, we have this kind of these guidelines down here to help guide that. So by what I mean by high N to Z ratio, I mean a value, so an N to Z ratio that is greater than 1, or greater than the number inside the band of stability, which we'll see in a moment. So, but generally, if it's greater than 1, then we should expect it to undergo beta decay, as you can see right there. Now, in the case that we have a low N to Z ratio, so the opposite is true, N to Z is less than 1. Oh gosh, I keep getting these. Oh yeah, it's less than 1. Okay. So in the case that happens, we should expect either positron emission or electron capture. And then for the last thing, before we go on to some practice problems, we need to talk about the band of stability. So now, as I mentioned earlier, I can say that if the the N over Z value ratio is greater than 1, we should expect it to undergo beta decay. Now, this is easy to say on the first surface, but in reality, this is not actually the case. So we can see if we were to say that N to Z is equal to 1, therefore we should expect to have the same mass number as the number, or sorry, not the same mass number, the same number of neutrons as the same number of protons. So this would be like, say, 12 over 12, and then whatever that particle is. So no line right here. This right here would be a stable isotope of whatever this X element is, so whatever it has a atomic number of 12. So while this is good and all when we're in these lower number, so in this lower range down here, that's okay, but as this number increases, as the number of protons increase, so does this line of stability start to stray away from this ideal 1 value. So the straight line is representing a 1 over 1, or just a ratio that equals 1, so where the neutrons are equal to the protons. We can see that this right here is the realistic band of stability. So as the further up we go in protons, the further away from the line we get. So we can see, using this little legend right here, the non-radioactive particles, or the non-radioactive points, I should say, are represented in this blue color, and we have the radioactive portions represented in this kind of green color. So this means if we have, say, elements with an isotope with a atomic number of 50 and look at that, an atomic number of 50 and a neutron count of 50, so 50, 100. This right here is radioactive, even though that it is 50 over 50, which also equals 1. This is still in the radioactive zone. So as we move on to the practice problems, you will see, actually I'm not sure if we will see it, but we need to just keep this in mind as we do more complex problems in the future, as this does stray away, the band of stability does stray away from the ideal 1-to-1 ratio. Now that we got the basics down, let's go ahead and move on to one practice problem, since I'm just about run out of time. So let's take in phosphorus 34 as an example. So first thing we should do, we can tell that this right here is less than 83. Z is less than 83, or not greater than, less than 83. So therefore, we can assume that this is not going to go undergo alpha emission, and rather it'll go under something else. So from here, let's go ahead and figure out what the N value is. Remember, this right here is the sum of the protons and neutrons. Therefore, we must, in order to calculate the neutrons, we must do 34, not protons, neutrons, we must do 34 minus 15, which equals 19. And now from here, we can go down and put this into our N to Z ratio. So that'll be 19 over 15, which is roughly equal to about 1.2. So as you can see, as we discussed earlier, this is greater than 1. Therefore, we are to expect that this will undergo beta emission, beta particle emission. So that's just a high energy electron from the nucleus of the atom. So in order to write this out as a nuclear equation, we're going to write 34 phosphorus is going to go, and that's going to equal a electron. So we can either write E there, or we can write beta particle. Either one's fine. I'll write beta particle here. Plus, remember that when we eject a electron from the nucleus, we are therefore creating a proton. So that is going to be +1 here. So instead of it being 15, it'll be 16. I don't have my periodic table right now, so I can't quite tell what 16 is, but I'll just put X here. You get the gist. This right here is going to be the final answer. That is it for this video. Thanks for watching.